everyone to this AMA session, which is an Ask Me Anything session with Professor Jayant Murthy. He's a senior professor in the Indian Institute of Astrophysics, and he has been working for more than 3 decades in in the space sector, on space missions, space astronomy, interstellar dust, and we are very excited to have him here with us and learn more about space exploration, space missions, and the stuff of space from him. So welcome, Professor Murthy, and we are very happy to have you here with us. The first question is that astronomy is such a vast field, right? And space also cuts across many disciplines. So what are the things that you're finding most exciting right now that is happening in space and astronomy? And what would excite current students and encourage them to enter this field?
When you look at what is interesting in any field of science, it all depends on what's the hot topic at the time. So now people are interested in black holes from light, or maybe solar planets. That's another exciting area. But if you're going into study astronomy or any science, then you don't go by what is the latest and greatest field. You go into something that it can be luck. It can be where you go to college, who your advisor is. And so the real interesting thing for us is the process. It's when you find out new things, how you find out new things.
I see.
And so in that way, any area of astronomy is interesting.
What are the exciting fields? And you were saying that you try to work on what your peers and your advisors working on, rather than what is the hottest field. Could you elaborate that a bit? Because the students tend to try to enter a field because of the hot topics, right? So
yeah, so if I were a student, I know that there are areas that interest people. And so very often the questions you get are black holes or strings or something like that. But really, it's just sitting there and the fact that you're learning new things. That's what students should focus on. Everything is interesting, whether biology, astronomy, whatever it is. Everything is interesting.
Okay, then let me ask you the question: what interested you in your field, right? To work on these various missions and interstellar dust. What interested you in interstellar dust, and what do you find interesting about it?
When I started, it was an accident of where I was. I was at Johns Hopkins, and it's a small department and limited number of faculty. I knew I wanted to do astronomy, so there were only 2 or 3 choices. I could work on planets, which I wasn't really interested in, or I could work on interstellar dust. We were working on space missions, and so as part of that, it was one of the things we were studying was interstellar dust. So when I started, that's what I was interested in. I knew I wanted to do physics. I knew I wanted to do astronomy because that's the way my mind works. I never, when I was a student, biology was a lot wetter than it is now. People were cutting things open, and you younger people, you probably never dissected a fish or a rat or a frog. If you do that in high school, it puts you off biology. Chemistry was too hard. So that left physics, and the place I went, it had a limited number of opportunities. So I work on interstellar dust, and there's always new things to learn about it. So now there's a lot of data available, and I use those data mainly from the Galax spacecraft, from Voyager, to study interstellar gas and dust.
That must be very exciting to get data from the Voyager and study, do your studies on that. how exactly then? What role is data playing right now, and new fields like AI, ML, and big data? How much of a part are they playing in this? Playing in astrophysics?
Astronomy, uniquely amongst all the sciences, rests on data. We are an observational science. We can't go blow up a star. And maybe that's a good thing. We can't go create our own planets. We have to depend on the data that we get. And now with modern instruments, you get more and more data and more objects. So maybe maybe 30 years ago, I would have studied a single star. Now I don't study a single star, I study hundreds of stars, or thousands of stars, or millions of stars. And so here is where statistics and machine learning are very important. Now, I've tried actually to have collaborations with machine learning people. And where it fails is that machine learning people have an absolute confidence in computers. They think that what is important is the models. And you see that in these epidemiological guys now. All these guys coming out with models for how the virus will spread. They don't care about reality. They just care about their models. And so I think there's a great opportunity for machine learning in modern astronomy. It's just that you need that combination of being able to do the machine learning and of being able to understand the data.
I see. So there is a need for a lot of collaboration between, computer scientists and astronomers right now more than ever, right?
There is a need for collaboration, but the language is different.
I see. So what then things in this decade must be certainly much better than when you were working before, right? In terms of collaboration, because now you can over the internet collaborate with many other people, and they can help you. There are probably certain open source missions and things like that who also run code on their computers to help decode some of the data collected by various space instruments. I think there are some of that.
What has changed since I was a student is that now data are readily available. I can go and I can get data on any mission I want. So like I said, I use a lot of Galax data. I'm using data from this Korean satellite, Spear, Voyager data I've been using for many years. So data are available, the publications are available. I don't go to a library at all now because everything I do, I read online. The collaborations part, now that gets more tricky, because we're all overly busy and we're all busy working on our own problems. And so when I want to collaborate with someone else, I have to find them at the right time. And getting to talk to people, it's still always easier when you know them personally, at least for me.
I see. Yeah, that kind of makes sense, because now with computers and internet, people have become more busy than before. Talking about the work that you're doing, and what are the major developments have you seen overall, right? What have you seen especially happen in the past few decades that you think is very crucial in astronomy and space technology?
So, of course, everyone knows LIGO, the discovery of gravitational waves. And that's huge, because now, previously, we were limited to optical astronomy. Optical, by optical, I mean radio, ultraviolet, X-rays, electromagnetic astronomy. So now, with LIGO, we've opened up this completely new area, gravitational wave astronomy. And we're still limited because our instruments are not very good. Eventually, people will go out into space. They'll detect gravitational waves going through space with unprecedented accuracy. So that's one. The second thing that I would say is very important is extrasolar planets. And ever since Kepler, our understanding of even our own solar system has been revolutionized, because we see so many planets, so many solar systems. We used to think that our solar system was typical. Now we know that our solar system is unusual. They're
Really?
very
Okay. Hey, how
many.
is it unusual?
Oh, we have when I learned about our solar system in college, what I learned is that the small rocky planets are near the sun, and then you go out and you have the huge gas giants, and everything made sense. Why do you have huge gas giants far from the sun? Because it's cold out there, and the sun's radiation has not driven out the gas. But now you find Jupiter's right next to the sun, or Jupiter-sized planets right next to the sun, or their own sun. So it's a whole variety of solar systems. Nothing looks like ours, where you have extrasolar planets and, extra Jovian type planets and terrestrial type planets.
I see.
Nothing looks like that.
I see.
And you have planets with 5 suns, you have 5 stars, and you have a planetary system. So that's incredible.
Yeah.
So that's but in data, what has really changed astronomy is that we're now getting data from larger and larger arrays, more sensitive. We're getting more sensitive data. We're going deeper into the sky. We're looking further out. Instead of getting hundreds of objects, we're getting millions of objects. And the volume of data. We've now got so much data that some missions cannot even store the data. They're getting petabytes of data a day. They just can't store it. They throw away a lot of it. And so that has changed.
Wow, that's very interesting. So it seems that computer systems have to evolve to be even able to explore space in the future.
Oh yeah, there's huge challenges. You need a fast internet? Even if you have a fast internet, is your disk capacity enough? There are huge challenges here.
I see. Very interesting. So we've gotten 2 questions already, so I'll go and ask those questions. Shubhojo is asking, I'm curious, what kind of things does Voyager measure? What data from spacecraft is available for scientists?
Okay, so I'll start with the history of Voyager. So it's the 2 spacecraft were launched in 1977. First came Voyager 2, and then came Voyager 1. And the reason was Voyager 2 went to all of the Jovian type planets, Jupiter, Saturn, Uranus, and Neptune, and then went out. Voyager 1 only went to Jupiter and Saturn. I hope I'm remembering correctly. And so their primary focus was to explore the outer planets. And the instruments they had magnetometers to measure the magnetic field. They had radiation particle sensors to measure the particle density, the radiation density, and so on. And the one that I'm interested in is the ultraviolet spectrograph, UVS. And so each spacecraft had this UVS on board. And what that does is it gets the spectrum, that is the intensity as a function of wavelength, in the far ultraviolet, from 90 nanometers up to about 150 nanometers. And that area is important because that's where you get a lot of the atomic and molecular transitions. So things like oxygen 6, which is 5 times ionized oxygen, that's a measure of 100,000 degree gas. So if you measure this line, you measure 100,000 degree gas. So that's what I'm interested in. You may have seen the other data from Voyager. Every few years, you get a note saying that Voyager has left the solar system. And so that's from the particle density, basically. Now, Voyager was unique. in that they actually allowed the data to be used for purposes other than the original mission. Most missions don't do that. We have a little bit of New Horizons data, but not very much, because New Horizons data has focused on Pluto and now on that on that Kepler belt object, Kuiper belt object, whatever its name is. So that you don't get this general purpose spacecraft. With Voyager, we actually did. And so that's the kind of stuff we did. Now Voyager is so far out that they're RTG powered, radioactive, radioisotope thermoelectric generator. Basically, they have plutonium. That plutonium is hot, and so they convert the radiation into electricity, and that's what powers the spacecraft. It's too far away to be powered by solar cells, and so now it's so far away that they turned most of the instruments off. But that's what we get from Voyager.
Okay, that is very, very interesting.
Oh, and all of the data are available. That was the second part of the question.
I see.
All of the data from Voyager are available, as they are from every NASA mission now. They're all available.
So
you may not know how to use it.
Right. So all NASA missions are making all of their mission data available for public use?
That's right. The reason is that it's basically right to information. The satellite, the spacecraft, is paid for by the taxpayer, as is my salary. And so whatever we do should be available to the taxpayer.
That's a great point. Same goes for ISRO, I suppose. But we'll get to that in a minute.
Sure.
Yeah. So the next question we have is from Raveen. He's saying, I'm interested in Betelgeuse's apparent dimming in the recent past. I've been showing it to my kids and they have newfound interest in stars and physics. Could you please comment on that?
The first thing I'll comment on is how you say Beetlejuice. So I always say Beetlejuice. And this is one of those tough things because it means, I read the discussion some time ago, now I don't remember, but it means something like star in the armpit of Orion. And so it's really Beit al something because it's the Arabic term.
Oh, wow.
But
okay,
I
I see.
Beetlejuice is the closest pronunciation to what we say. But we've all been excited by that star because it's as dim as it has ever been. And so Betelgeuse is a red giant. And what happens is that it's a much heavier star than the sun. And so the outer layers, the inner layers, what happens is that first you have hydrogen fusion, and then after hydrogen you have helium fusion. With our sun, it'll stop sometime around helium fusion, maybe a little bit of oxygen and carbon fusion. With these heavier stars, they continue on past carbon to do neon and whatever else comes after that, until eventually they come to iron fusion. Now, when they do iron fusion, then of course when iron fuses, it absorbs energy. So when it absorbs energy, then the outer layers of the star will collapse in. They collapse in at something like 70% of the speed of light, and then it'll rebound, and that's when you get a supernova. And so that's what will happen to Betelgeuse within a few years, where a few years can be anything from from tomorrow to a million years in the future.
Oh,
so these kinds of stars, they always contract and expand. When they contract, their surface area gets smaller. And so the star, you see, the star appears fainter because there's less area. When it gets bigger, as it shrinks, it heats up. And then when it heats up, it expands. And then when it expands, it gets brighter because the star itself is so much bigger. So you're seeing a larger surface area. And so that's what we see with Betelgeuse's variability. Now, apparently, and you have to understand that I'm only repeating what I read, Betelgeuse, it has these regular cycles of expansion and contraction. And so it just so happens now that two different cycles of contraction are coinciding. So this is just part of a 100-year cycle where it now looks much fainter.
Oh, okay.
But we
I
never
see.
know. It doesn't mean that it'll be a supernova tomorrow, but it will be a supernova at some point soon.
It's headed that way. Okay.
Well, it will be. It has to go that way because it's a huge star, and
Okay.
that's the way huge stars work.
I
But
see.
it's not necessarily connected with this particular dimming and brightening.